Howdy, everybody. Hope you're doing well, wherever, whenever you are. We're here for the recap 2016. I haven't read all of your comments, mostly because I'm releasing videos a little earlier, but the comments I have read have been great, and so um, you'll see some changes I made based on comments. So always keep those coming. Love to see how you solved it or different ways to do it. Um, and yeah, it's not that I don't read comments. I definitely read all the comments. It's just the way that I'm releasing this so I can get ready for the upcoming everybody codes and stuff means that I don't quite get to all the comments, but keep them coming, and I'll keep refining this stuff, maybe add some notes and things as stuff changes. Anyway, I thought this year was a good year. It felt like it went a little bit easier than the previous year. I think one of the previous years I just had a couple days where it was like there was nothing. Excuse me, there was just nothing. I didn't know anything about the problem, and I had to kind of like fumble my way through it. But this year wasn't too bad. You can see I'm able to like finish the whole thing in less than a second. Some of them, though, to be clear, you'll see different multiple solutions for each day if you like run the code. For example, day 24 or day 16, you'll see the difference between a normal P2 and using the Chinese remainder theorem, stuff like that. So anyway, we'll definitely talk about those things in the recap. So, I guess with that, let's just get started. So the first one was day 1. There weren't a ton of changes to this one, but I thought it might be interesting to like test different things. So I added an int type and swapped between the different ints, like i32, i16, isize, things like that, just to kind of test it. If you remember, this day is you're going around a grid, and in part 1 you want to see where you end up, and in part 2 you want to see the first time that you overlap, I guess, hit some place you've been before. So you're doing a lot of integer addition and subtraction, stuff like that. So I thought I'd just try isize versus i32 here. The i32 was marginally faster, like 3 to 5%. So if that's something you're worried about, i32 is probably the way to go in general, unless you need a larger value like an i64. This is kind of an interesting thing to think about. Like, your intuition might be, oh, I should just use isize or usize. At least that's my general intuition. The idea being, surely I should use the native instruction sets, size for an integer. But modern PCs these days, and CPUs, I should say, it'll depend on your CPU, but most of them have, long-standing, very performant operations that work on 32 bits, and even the 64-bit processors do. And depending on how many calculations you're running, 64 is greater than 32. So there can be a penalty there in having like the double width, twice the width. It does affect things like memory and stuff like that too. That's something to think about. I think in general for these problems, it's not going to make a significant amount of difference. Again, it was just a few percentage points faster, and we're talking going from like 5 microseconds to 4 microseconds. I added a benchmark where I run it a bunch of times and then do the min max average. I guess I could do that right now, just so you can see what I did. So here it is with an isize, or an i32. It's going to run this one 100 times, this day 100 times, and test the durations. So you can see like 12 and 14 microseconds. If I change this die size and run it again, we'll give it a minute to run. So you can see on part 2, oh, it's actually marginal. Yeah, this is what I expected. It's like just very barely worse. If you run it enough, you're like, oh, it's just barely worse. Again, we're talking microseconds here. Probably not a big difference. Anyway, that's something to keep thinking about. Another thing that I changed in here, remember you change directions. And I used to have this helper function that would like do the deltas and update my direction. One thing you can do though is you can do an add or an add. You can impl an add or an add assign for anything, right? Normally you'd presume it would be like for your own same type, right? And by default it is your own same type, right? So the presumption is you're adding your own thing. That is, you'd add an integer to an integer, but there's nothing that says you can't add a character, at least from the Rust point of view. And so that's what I did here is I said, oh, impl add assign. So give me a character, I'll match on that character, and then I'll update this. And this came from, I think we figured this out. I don't remember if we figured it out in the video or not, but commenters definitely helped me understand like the way that you turn left or right is you swap your X's and Y's. And then if you're going right, you negate your new Y value. If you're going left, you do your new X value. So that's just something to keep in my pocket to remember. But anyway, now that I have this add assign, I can do something down here where I say my direction plus equals my direction. And if you look, like this is a point, so an XY point with integers, and this is a character. So I can add assign to a character. Because Rust allows you to sort of obfuscate what a value is if it can infer it, you may not recognize that this is a character that you're adding to a point, which is 2 integers. And it is something that I found a while ago when I was doing work in like C++, especially the fact that you can like impl these operators for anything. From anything to anything can sometimes feel a little weird, right? And you can do any in these languages, you can do any of the operators, right? So I could have impled sub assign, but had it be the equivalent of an addition. And so I would often, this is all to say, I would often see in code that just sometimes things didn't make sense. And it made it confusing from a readability perspective. So, does this feel less readable? I don't know. You're saying the new direction is equal to this given to the update my direction based on the given direction. That seems fairly readable. But again, I'm the writer, and so the reader is not me, it's you. You'll have to tell me how you feel about that, and maybe just what impls in general. It's very common to have like a mul based on an int type. That's very normal. You're saying, you're scaling is the way to think about it. You're scaling your point to some, or a vec 3 or whatever you're using. That seems relatively normal. Adding and add assigning, where you're literally doing adding and adding assigning, makes sense. So these things I think are totally normal. So if you're saying I have a point, add another point to it, that I think someone who's reading that can make sense out of it. This one probably less so, and so you just have to decide where's your line of saying we've crossed too far into the unreadable. So anyway, that's just something to think about. I also tested P2. One way I was able to speed it up is to give it a capacity. So if I start with an initial capacity, it doesn't have to like reallocate a few times. And that actually does save about 25%. It's crazy how much time it saves. So that is something to keep in your pocket if you're doing something that you know is gonna, I'm gonna use a hash set and it's gonna have 5,000 things in there. Adding that in there, adding the initial capacity may help. Now it won't help if you alloc 5,000 of them and then you only use 10. That may not give you anything. In fact, it may take more time because you're only using 10. So just keep that in mind. You kind of want to find the sweet spot of, based on your input, what is this number likely to be? And then you can get like some minimum value. So this is a little thing you can do if you're looking to improve performance. I did try Vec2. That's just something always to keep in mind when you're going for performance. This day one thing, it was kind of about the impl add care, but also like what kind of performance things could I do? And this is one of those where sometimes a vec is faster. Like it's faster to search through a very small vector, a very small array, than it is to hash the value and check the hash set against it. That was not the case this time though. So that's just always something, again, if you're going for very specific performance and you know that the total size is going to be small. In this case, I think the size ended up being somewhere on the order of 200. I don't remember. It was day one, right? Day one, part 2, 116. So there's 100. There were like somewhere on the order of 116 in here. Checking if those have been seen is slower than using a hash. But if there were only 10, 12, 15, maybe even 20, 40, it may actually be faster just to use a vector. In the long run, again, these are solving in like 17 microseconds. So probably not a big deal. But if you're really trying to eke out performance, those are some other things you can do. So day 6. Oops. Let's see, what did we change here? Okay. This was a cool comment. If you're doing, if the only thing that's changed is like your comparison operator, which happened to be this part, in this day, you're given like a list of strings and you want to do a frequency map of like the columns. So I do that once in my parse input, and then I just solve. I call this solve by comparison, and I pass it a comparator. And so you can see this is a cool thing you can do in many languages, even in like C, right? You can technically pass higher order functions in C and stuff too. But here I can say like, oh, give me some. My solve function says, give me some function such that I can compare two U sizes, and then I will sort by and collect and find the max of each one to get my, I think it was you're looking for a password in the end, right? And then for my solve by comp, I can just use usize comp, and for this one I can just use this reverse right here. So that's a cool comment. Something to think about is I mean, depending why and where you're solving, but from a readability perspective, this seems cool to say, oh, I can, in a single function, I can, you can give me a comparator, and then I'll compare based on those two things. And then part 1 and part 2 solve the same way. The only difference being how you compare those two. So I thought that was a cool way to do that. Day 8. Oops. So this one was you were like building a grid, if you remember, and you were like they had instructions on, do you want to like shift columns or rotate columns or rows, and based on that you'd eventually end up with a password that you can read. I think this one came from a comment too. For rotate row, you can actually just call rotate right, because you presumably have the row and you just rotate however many times you're told. And I actually use rotate right in a future day, but I didn't use it on this day. And so that was a good thing to point out, is you don't need to implement that yourself. And what that means is I can do the same thing for rotate column. So here's my rotate column function. Basically, I get the column, I rotate it, and then I update the values. And this was a cool thing that came from a comment as well, right? Is like I can do an iter mute of the pixels in the column and zip that with my new column so that I can like say, hey, update this value to be the new value that it should be, which is kind of a cool thing to do. So I have a mutable iterator that's zipped with my new values, and that allows me to do something like this. So I thought that was kind of cool, a cool thing to do. I don't think I've ever done anything like this before, so that's kind of a cool thing to think about. What else? Oh, I could also use this fill operation, right? So I think I had an inner loop here, and so instead of an inner loop, I can just say, oh, fill in whatever's missing. The one thing that I did change about this day, I don't know if you remember, but what it is you get a screen output, and it like you can look at it visually and see what it should be. I added this decode message function, and it is really cheesy. Basically, it says for each of the you call this decode thing, and it basically goes and gets the blocks out and then compares the blocks to these things and giving these. It is not at all exhaustive, right? So this may not solve it for you, but what it does mean is like my day, what is this, day 8? I actually get the password out, as opposed to, a big block of text that has the password, if that makes sense, over here on this side. So there you go, day 8. Day 9. This one, I think the only thing I did was split at. This was a cool function. I don't remember how I had it before, but I know how much I want to split. So if you remember, this day is you're like, you get things in parentheses, and that tells you like how much to duplicate like the next n blocks. Well, if I know what n is, I can just call split at n, and then I can do it, and that magically works. So that was kind of a cool, simple thing. I think what I was doing is like getting slices. Like I had a slice for my inner, and I had a slice for my rest. I would like slice the thing, but you can call split at, and that returns those 2 slices for you if you know the length. So there's a whole bunch of splits that are really cool. I think this one was the one too where there was the potential to do this in a state machine, and I really tried to get it to work in the state machine, but it was never faster. At least for me, these split onces and split ats are pretty fast, right? You can think essentially what I'm doing is I'm like simplifying the state machine by saying, hey, jump to here, jump, and then, split this chunk, and then, jump to here type thing. So for me, this ended up being faster than a state machine. But if you solved it in a state machine, I'd love to see what your state machine looks like, so I can like compare and contrast. My state machine was doing it based off of a character iterator. So maybe there's still ways to kind of like jump around within the state machine. You're doing the equivalent of this. You're just tracking the state of, am I in the paren? Have I gotten the whole paren? And then, do this recursively or not or whatever. So anyway, that's day 9. Day 11. Let's see. This one I actually think, if you go look, had the most changes. And why is that? This, I don't know if you remember, but this is the one where you had like some very funky rules about a chip and a generator, and they had to like be together, and you were trying to move them all up to the top floor so you could like build a microcomputer. We did eventually get it solved relatively fast, and the way that we did it was our initial implementation was just try all the neighbors, and that was pretty slow. It took a few seconds. What we did, I should say the way to solve this is to use like a BFS of all the different states. So like if your elevator's on row 1, and there's 2 items on row 1, then you can either move one or both of them up or one or both of them down, right? Is maybe the way to think about it. Those are your neighbors. And so you just do a BFS to find the first solution where you've got them all up on the 3rd floor. Our initial implementation took a few seconds, and then we found a Reddit post, I think, that talked about some hints. And the major hint was all of the states are any state where you have 2 generators on the 2nd floor and 2 generators on the 1st floor. It doesn't matter like or I should say a chip and generator pair. It doesn't matter if like the L pair is on the 2nd and the M pair is on the 1st, or vice versa, is to say those states are equal. So I implemented it a little bit like this and a little bit like, I implemented this and this to do that hashing that allowed me to like solve for it faster. And that helped us get down to like, I don't know, 100 milliseconds or whatever. The thing to think about is when you're doing a BFS, you're going to visit like nodes and it's going to grow exponentially. So the more neighbors you have, the harder it's going to be to visit all of those nodes as you're expanding. So if you can do things to prune, then like the thing grows smaller and you have fewer nodes you have to visit before you get to the end. And so this was the biggest optimization that actually did that for the problem that I felt comfortable finishing. There were several other solutions though, or several other optimizations. And so that's what you can see, this successors function. It is substantially more complicated. And basically what happens is we collect how many can go up, how many by themselves, how many can go up in pairs, how many can go down by themselves, and how many can go down by pairs. I won't go over the logic, but we're collecting all of those. And then we're going to, once we have collected all those, we're going to compare, like we're going to prefer going up, and we're going to prefer going up with 2 as opposed to 1. And we won't even give the BFS search these single ones if there's an up double, if that makes sense. So the idea is to very much prefer going up to going down, and that potentially what it does is it adds the states that are bringing us closer. There is an argument that you could use A* here to kind of help you with these. So what is A*? A* is just a BFS, but you like prefer to choose nodes based on some sort of heuristic, but I could not find a good heuristic, and it actually never led me to the right answer. So this ended up being the only way that I could find to do it. If you did solve it with A* and you found a good heuristic, I'd love to see it. I could never get it to work with my input solution. So anyway, that was kind of the big change. But then the BFS itself doesn't actually change for part 1 or part 2. You still do the BFS. I've just now pruned back the branching of the BFS, and that's made it substantially faster. I asked, this one was a funny one too, because I asked AI, like, how would you optimize this? And it flailed all over the place almost every single time. It was like, oh, I'll use A star. And then it didn't get the right answer. And I'd have it iterate on A star heuristic for a while. This was after I had tried it myself. Could not find one. In fact, I don't think, yeah, it was never faster and it was never the right answer. So that was kind of hilarious. This is one of those problems where it's not clear to me A star would ever work. So I then asked it about, like, can we do things to fix these successors? And many of them couldn't, but I think the Claude model did find a couple of these things like this that actually sped it up somewhat. So it could get there if you like really told the AI to focus in on, here's what I want you to do. I want to do the branching with pruning type thing, or the BFS with pruning, and that helped it like find some of these optimizations. So there you go. I think that's that for day 11. So the next one is day 15. I don't think this one I had to change my code, but I do want to talk about more about the Chinese remainder theorem. This is one where like my math was not great. I'll keep a link to it. The thing that you have to remember with these math solutions is it's not always a copy and paste. So just a reminder, like, what is the theorem? The theorem is like, there, if you have a list of congruences of like A mod n, you can do some math to calculate what this X value was. And we had actually done that and solved it. I don't know if you remember, but I was still getting the wrong answer. And why was I getting the wrong answer? It was because I was not like turning the solution into the right. I was not turning the problem into the actual Chinese remainder theorem. Because remember that, so what it is you have like a bunch of disks that are either open or closed, and they open at different intervals. You want like the ball to drop at the point where each of those are open as it's falling through that hole. And like what I had missed was this, my list of congruences right here. So the thing to like keep in mind is like, at least for me, was, okay, if I know it's the Chinese remainder theorem, like this is what I'm solving for, but or this is what the general algorithm is solved by this, but I may not be solving for X, right? I wasn't actually solving for X, I was solving for T. So I had to do some math to figure out what T actually is. And that's what this math does here. I think maybe I can show, maybe I can ask, let's see. I wonder if one of them will solve it for us. Sorry. Okay, let's see what it says. But the point is like, and this is where I failed to like find the thing. I saw early, oh, this is a Chinese remainder theorem. So I'm sure some of you are better at the math stuff than me. It's just something that was important to me to like note, and that's why I want to highlight it here. If you think it's a math solution, just make sure, think about what you're solving for and make sure what you're solving for is what you want. So, and this is the part right here, right? Is like, we're actually solving for time right here. And The time is the negative pk plus k mod nk. So this is much different than the original, which would be like x equals k mod nk, or sorry, like ak mod nk or whatever. So you would definitely be using, I guess that the point is like make sure you're getting your math right. And here they're kind of explaining it. You know, your time changes over time, and so you need to calculate that time appropriately. So that's what is happening here. Is I'm saying, oh, calculate this right here, and that will give me my m, and then my remainder, which I think in this case is my well, it's my solution to the thing, and this, my congruence contains this constant and then this modulus, if that makes sense. So but then it will solve for it. So there you go. Anyway, I won't speak too much about that more because, you know, again, the math stuff is still not my forte, but that was one. Let's see, day 16. Oops. If you remember, this one was the dragon curve problem. The idea is you start with a set of bits and you're going to expand it in a way where you like take this chunk, flip it, reverse the bits, and then add a 0 at the beginning of it. And you do that until you get the disk size, and then you calculate a checksum based on that disk size. So let's see. I believe I knew what the checksum was. Like I actually figured out the checksum. I was like, oh, you actually don't need to do a checksum and then a checksum and then a checksum and then a checksum. The way it worked was you kept doing checksums, and the checksum would shrink the size until you got to an odd length checksum. And so I think when we were doing this, I actually figured out that, oh, I can actually do a single checksum by just like figuring out how many chunks of the original string are in the final checksum. And because you're doing like this XNOR thing, you really just have to figure out how many of them are ones. And so that's what I did here. And that actually doing that, as opposed to like iteratively calculating the checksum until you got to the thing, turned out to be the fastest way to do it. I had alluded to the fact that there's probably a way to figure out the total number of ones for a chunk programmatically, so you don't actually have to build it by hand. Because what was happening right here is, you see, I actually build it by hand. So I like keep track of my current state, and then I iterate over the characters, reverse it, map it, collect it, and push the 0 and then the flipped thing. And I do that over and over again until I have the size that I need. It turns out I was right. I just wasn't smart enough at the time to actually do it. But I think with some help from AI, I don't remember how I helped figure this one out. I was able to solve it with this checksum calc. And so what this does is, again, the way that you figure out the checksum is you just need to know how many ones are in the original inputs chunk that would be calculating that. So how do you describe this? Let's say there were 100 in the original input, ones and zeros, and that would eventually boil down to a checksum of 10 or 5, let's say 5. What you know then is like each chunk of the original 100 is going to be of size 20. And so you just need to know how many ones are in those first 20. And the way that you do that is you can kind of, like I said, you can, because the way that the algorithm works, it's only adding things to the further out in the string. So you just need to keep adding stuff to the end as you're doing that. And that's actually what happens here. So you can see I have the original value, the reversed value, and then I do some math to figure out how much each chunk is going to be. This size and size wrapping neg is actually kind of cool. Basically what this does is it, like, the wrapping negative, like, is basically taking the negative of the size +1 or something like that. You can look at the details, but what this does is it's doing bitwise operations to determine how big each chunk is going to be. It's like shrinking down that size based on how many chunks. And then I know my length based on my total size divided by the length of each of my chunks. So now I know how big my sum is going to be and how big each chunk is that's going to contribute to each of my sums. I'm going to keep a buffer that contains any unused data. And then I just need to track these two values, the total number of dragon flips I've done and what the parity is of the previous iteration that I've done. And the reason I need to track this is because if you think what's happening is I'm going to take this block, I'm going to flip it over and put it right here, and then I'm going to swap the things. So I need to know how many times I've done that, because that will infer what the original and the reversed look like and what their parity is as I'm going through it. So basically what I do is I just go through each of the sums, right? For the length of the sums. And I just ask myself, do I have any buffered left? And if I do, I take the rest of that. And then I figure out how many ones and how many ones are in that buffer that I already have, and how many times I've like dragon rotations I've done in the thing. I track the dragon rotations by this none. So you can see this is actually an option bool, and like that middle 0 is treated as a none. It gets added in the end, I'll show you, but the idea is that helps me like track how many dragons I've seen in the thing. Then I just need to figure out how much do I need to fill the remaining buffer so I can get enough to calculate this part of the sum, and that will tell me how many dragon groups I need to create. And so I update my dragon count and my ones count based on those values. And then anything I have left over, I need to now add back into my buffer, my temp buffer. So I'm going to create I'm going to do a dragon rotation on it, and then I'm going to, take the remaining and add that to my ones and dragon. I'm going to pull out from the vector what I need to update the number of ones and the number of dragons I've done. So at this point, like right here, I now have figured out all of the ones that are going to be used for my checksum for that part. And I've maintained like this buffer that contains what I have left that will be used in the next iteration. And then I could just literally do some math and say, update my parity. And based on my parity, that may change how many ones I have. And then I just return, are the ones a multiple of 2 or not? And I think I actually do something very similar in my original solution right here, right? So if it's a multiple of a 2, I'm going to return a 1. Otherwise, I'm going to return a 0. Anyway, so this actually runs substantially faster. Are we on day 16? No. Yeah, 16. So you can see part 1 solves in 9 microseconds. Part 2 solves in 5 microseconds slower. Or sorry, I should say part 2 is faster than part 1. Part 2 uses my speedier way, and part 1 uses my originally way. And the difference in size is enormous, but this part 2 actually finishes faster than part 1 doing it the naive way. Anyway, so substantially faster. I'm solving in microseconds now than in I think it was milliseconds. And again, why is it faster is because the previous way is I had to actually build the string and allocate all the memory. And then I could, chunk it up and do the checksum like this part right here. But this is much faster to do it this way. It's actually not faster to do it for part 1 because you're doing a lot of math and a lot of tracking and buffer manipulation. And the size of part 1 is so small that it doesn't make it worthwhile. But for part 2, it definitely does because it's very big. And you could imagine some input that was like substantially larger than this, where you might not be able to fit it in memory on disk. You'd need to have something like this to do it for you. In fact, you could even... no, I was going to say you might be able to do something like this, but just keep the part of the string that's interesting to you, which is essentially what I'm doing, but I'm only doing it like a chunk's worth at a time, if that makes sense. So anyway, that was the optimization. Again, I didn't figure this out 100% on my own. I kind of worked through getting it set up and saying like, oh, here's what I want to do. But then it wasn't totally clear to me like how to, I think what it was that the AI helped me with was this parity, right? The parity is going to be changing as you're adding dragons. And that's going to affect the number of ones, is the way to think about it. The idea is, think about when you're doing the dragon thing, your ones become zeros and your zeros become ones. So as long as you're within like a complete dragon, like let's say if the chunk was a complete dragon, the number of ones and zeros, the number of zeros on this side is equal to the number of ones on this side. Does that make sense? Because you're flipping them, so they're like, these two are like complements of each other. And so you just kind of, for each of the total dragons, you can actually just do that, right? You can just say, oh, the number of ones is actually equal to the number of zeros in my other thing. And so, you can do some simple math there. It's just that remaining part that was struggling that gives you like these parodies where you don't get it all. And so you had to kind of have to figure that out, if that makes sense. Okay, let's see. I think that's probably enough for day 16. A lot of talking about day 16. Again, probably not necessary, but it was a fun exercise for me because I could kind of visualize in my mind that you might be able to do this, just not, I didn't know how to do it. So there you go. Next one, day 17. Day 17. Not a lot on this one. If you remember, this was, you're in like a little box and you kind of need to find, based on every time you move into a new item. It's a small grid. It's like a 3x3 grid, but every time you move, you do an MD5, and that determines like which doors open or close based on where you're at. And the solution was to just do a BFS. I looked for optimizations for this one, and really, okay, so part 2 was what is the longest path you can take to get to the end. And the only thing that I could find to speed this up is you don't actually have to track the visited nodes. So it used to be like a normal BFS is you track and say, have I visited this? And if I haven't visited it, then I add it to my list. If I have visited it, I know I don't need to try it again. That keeps you from like falling back into a circuit or a circular check that you've already been. In this case, though, because my list of like visited nodes is in the MD5, the MD5 implies uniqueness because it contains part of the MD5 contains where I've been before, and presumably as long as we aren't like hitting duplicates in the MD5, which is highly unlikely for this small of a puzzle, but that implies that each MD5 is going to be unique, so I don't actually need to track a visited node. And that did save like 25% of the time. Again, it was not a lot. So you can see here for part 2, it takes 22 milliseconds. And so maybe it was like somewhere on the order of 30 milliseconds, somewhere in that area. It did save a little bit of time, but not a lot. So not a huge change, but definitely it was something that, anyway, it was something small that I found. So, okay, the last day that I want to talk about, day 24. If you remember this one, you're given a giant map. Maybe I can bring it up. You're given a giant map like this. Sorry, it's an eye chart. How far can I go and you still see it? So this. And within the map, there's like, here's a 3 right over here on the right. It feels like an eye chart for me. Here's a 2. You're given these numbers, and these are where you need to oh, here's the 0 up here in the top left. Sorry for the eye chart again. But the idea is you're given these places that you need to go in this maze. And so and what it's asking is, what is the shortest distance you can, shortest path you can take to visit all of them? And the only difference between part 1 and 2 is what's starting at 0, visit all of them, go back to 0. What's the shortest distance to do that? And this is one of those like 2-stage things I think I had mentioned. So for the first stage, you can literally just do Dijkstra's for each of them. So you say, you know, from 0 to 1, do Dijkstra, 0 to 2, 0 to 3, so on and so forth. Do Dijkstra for all of them. All, you know, like the product of the two, A times B, Cartesian product of both of them. Do Dijkstra's, and now you'll have a map of the distances, and then you can do a min on all of the permutations. And that solves pretty fast. Let me find day 24. Yeah, so down here you can see it solves in 20 milliseconds, and this one solves in 21, I think. Not too bad. I had mentioned though, so here's like, again, I'll show you the code really quickly. Part 1 and part 2 again are the same. The only difference is we check how far how to get back to 0. So you can see here is where I do Dijkstra on all on all the product of A times B, and add those values to a hash map, and then I can do, hey, give me all the permutations of all the locations, and then sum up their distances and find the minimum. So this permutations, again, was small because I think there was only 8. And in part 2, there's only 9. So it doesn't take super long. You can see the part 2, the only thing that changes is I need to start at part 0. And then once I've gone to the end, I need to calculate my distance from the last item to back to 0. And I want to find the min of that. I had mentioned there's another way to do this, and it's called the Held-Karp algorithm. So just in case you aren't aware, this is totally a traveling salesman problem. And this stuff has been studied a ton. We know a lot of stuff about it and how to solve it. And a long time ago, Held-Karp Held and Karp solved this problem and said, oh, we can actually find a more efficient solution if you're willing to do this, if you're willing to use additional memory to help you solve it. And it's not helpful for small problems. So for example, I've implemented HeldCarp for our puzzle input, and you can see it only solves it marginally faster than this one, right? So here's my P2 normal solve. Doing all permutations takes about 21 milliseconds. If I do HeldCarp, it takes about 19 milliseconds. Only marginally faster. Where it changes, maybe I can show this to you. So here's the 3 solutions, part 1, part 2, and part 3. Where it changes is when n becomes larger. So right now I'm doing just the normal input, but I think I have a, is it called worse? This one I've added 4 more destinations. So it goes from 8 to 12. And we'll let this run because it's going to take part 1 and 2 somewhere on the order of 20 seconds to run. But you'll then see how fast it is. And I'll show you why. Let me create a Google Sheet to show you while this is running. So if our n is 1, 2, this, here's our value of n. I'm really bad at this stuff. Huh? So here's our n. This is our n factorial. Oh, you see it finished. So part 1 and 2 now with 12 take 20 seconds to run, but this one solves in 48 milliseconds. So what is this? It's equal to, is there a factorial? A1, no, A2. Yes. Okay, you can see these numbers get very large, right? Can I show this as that? I don't need zeros though, do I? Okay. HeldCarp solves in n squared plus 2 to the n, I think is what it is. We were just looking at it, weren't we? N squared to the n, yeah. So this is equal to a2 times a2 plus 2 dot, is there a power? Autofill. Okay. So you can see in these early numbers, there's just not a large difference. Even right here, you might argue, oh, this, did I do this right? Yeah. 40,000 versus 320. Why was, like, this is the problem we were trying to solve right here. Sorry, is this an eye chart? I'll zoom in here right here too. Okay, can you see this? Hopefully you can see this. So here's where we were trying to solve, and you can say, oh, HeldCarp only is order 320, and this one is 40,320. Why did this one? Why did they finish about the same time? The cost of doing this is very small. Like each iteration is very small. Each iteration here is like relatively more complex and requires more memory to solve it. So it's not when you start getting down here that suddenly you're all like, okay, this does have a big difference. So our n equals 12. When I added those to the puzzle, I added additional points of interest, like locations. We're now in the 479 million versus 4,000, and suddenly that does have a huge effect. So here it is right here. So this is all to say, it's something worth thinking about. Having held carp in your pocket is probably good. And when you ever say, oh, I'm doing the traveling salesman problem, or you can say this boils down to the traveling salesman problem, you ask yourself, is n large? And if n is large, held carp is going to solve it faster. I would argue that somewhere in the 1 to 9 range, maybe even the 1 to 10, is not a big deal. It's once you get into these like 11, 12 and more that it becomes a big thing. Now, I should say, remember, it requires a lot of memory to do this, and I'll show you why in a second. But just be clear that for extremely large ends, it may not be solvable for either of them without doing some funky memory stuff. So how does the algorithm work? Here's the algorithm itself. And essentially what you're doing is you're creating like a set of, a bit set of distances, and that, let's see how to say it. You're creating a set of the distances of a bit set that you visited and the last one that you visited. So the idea, you're actually creating a map. Sorry, it's a map. So you have a map that says, here's all the nodes that I visited, and here's the last one I visited, and here's the smallest distance I found so far. And you're slowly going to go through and add additional values to that map based on previous values in the map. And as you find smaller ones, you're going to update those smaller ones. When you're done, you're basically going to have a map that contains the shortest distance from every subset of the paths. And so the way that you solve it then is you say, okay, find within that map, find all of them that go from my start location back to my start location. And only keep the one that has the smallest distance. So why is this faster? Because you actually are only dealing with, and this is why the number looks funny, 2 to the n squared. What you're actually doing is you're creating subsets, and you're finding the distance of those subsets plus 1, right? So you start with a subset of just like 2 of the points, and then you add a third point, and then you add a bunch of third points to it, and you know those distances. And then as you're consulting the fourth points, you can go look and say, how long did what is the shortest of the third points of my bit set, if that makes sense. So here it is in code. We'll walk through it really quickly, just so you can kind of understand how it works. But I definitely needed help on this, if that makes sense. I totally needed to, I spent time looking at the algorithm, trying to solve it. I think sometimes my bitwise operators I had wrong. Anyway, it took time to work out, and I just need to get better at implementing this more often. So we'll look for future problems that say held carp, and we'll try and re-implement them. But here's the gist of how the algorithm works. I do the exact same thing as I did in the previous parts. I'm going to build my distance matrix from by doing Dijkstra to each of the points, and then I'm going to use those distances to help me solve it with held carp. So I need to know my start location and how many ends. This was just like a shortcut, so I didn't have to type location ends a bunch of times. And this is my dynamic programming matrix, right? So it's going to, this is the hash map that's going to say, here are, the key is the mask, which is a bit mask for each node visited, and the last node I visited, and the minimum and that will contain the minimum distance that I visited, that I've solved that in the past. So I start with my base case, right, which is like I'm at the start, I've only visited the start position, and the cost to get there is 0. And now I'm just going to iterate through, this is what it literally, all the possible subsets. So I'm building subsets of 2, then 3, then 4, all the way up to n. And they're all, just to be clear, this is why it is memory intensive. I'm storing all those distances in this hash map. So that's what the high level algorithm is doing, is I'm iterating through all these subsets. I have to, and so what this is saying is I'm going to iterate through all the masks from 0 to 1 to the n, right? Like all, for all the things. The idea is I will have checked all of the various possible subsets. So what do I need to do first? I'm going to go through the last visited of the location. So this is like, think about the idea here is my last is going to be, okay, for each of my masks, I'm going to try and add an unvisited node to it. And so I'm going to go through that list. Obviously, if I've already visited, I can then skip. Now I want to go check, have I already done this before, right? So if I haven't done it before, there's no need for me to do it, and I can skip by. That's a sign. This should never happen. This will always be the case that you'll get into here. But the if let sum is a way of saying, get me the thing, I guess, without failing weird, if that makes sense. But this should never happen because I'm iterating through all the masks. I'm always going upward. So I'm going to consult all of the ones, the distances, or the where I've only visited one location, then 2, then 3, and so on. So I should already know all of the 2s before I know all of the 3s, before I know all the 4s, so on and so forth, right? So basically, what do? I ask myself now that I've found that previous distance, I ask myself, for each of my locations, what happens if I add that node to my distances? And I'm basically, again, this is where the n squared comes from, is right here. This is where the 2 to the n comes from. So the n squared is I'm going to have the last visited node, and I'm going to have my next visited node. And so what I do is I say, oh, well, if this is already in the mask, obviously I don't need to do that one. I can skip through it. But otherwise, now I'm going to add this to my list. So I'm going to update my mask. I'm going to calculate my new distance. I know my distances from above. And then I just add my current distance to that new additional distance. And now I add that entry in there. If I found the entry, right, I want to return the minimum because I have a new minimum way to get there. Otherwise, I just add it to my list. And that's what I do, right? So I'm literally going through all the subsets. As I go through the subsets, I'm going to look back in the past and say, like, say I'm at length 4 now. I'm going to say, how many of the length 3s have I seen and then I'm going to say, what happens if I add all the length 4s to all the length 3s? And that's going to, I'm going to update all those values to the minimum. Then when I go to length 5, I'm going to be able to consult all of the length 4s and say what was the shortest way to get to these things when I add that bit mask together. So what do I end up with in this bit mask is basically the distances from any subset of the points. So if there's 6 points, there's, a bunch of lengths of 6 in there, a bunch of lengths of 5, and so on and so forth. Maybe the way to think about it. So now that I've done that, what do? Well, I just have to go through all my visited nodes, and I want to filter, I have to end at the start. So, I want to filter ones where I'm not in the start, I guess is the way to think about it, right? And then I want to get the value of only the ones where all of them are visited, right? I'm only interested in all the ones that I visited before. there's a whole bunch of them in there where I've only visited a subset. So I only want to consult the ones where I've visited all of these, and then I'm going to map that to my distance. And again, for part 2, it's not just this distance, but it's my distance also going back to 0. And then I just find the minimum of that, right? So this is going to give me my distance for each of my eyes, which is this, right? I'm going to go through all the 0 to n, find them all, find the minimum where all of them are visited, and then return that. Okay, that was a lot. Hopefully it makes sense a little bit. I've still only I've read it a few times, implemented it once with some help. So I definitely feel like I have a lot more to learn as exactly the details of how it works. But this right here is largely based, again, on this right here. Right? Here's the this chunk is the n2 to the n chunk, and this chunk is the n squared chunk. And the idea is go through all the distances, go through all the subsets of visiting all those nodes, keep track of the minimum distances, and now you've got a potentially faster solution than just doing all the permutations. So there you go. That's all the days. Again, I don't think it was that crazy of a year. Some of the algorithms that I could have used and maybe didn't do very well at, Chinese remainder theorem, the Held-Karp algorithm, didn't seem to be necessary for this day. I know that changes in future years. There's some years where if you just don't know Held-Karp, it's going to take you like 3 hours to solve the problem. And I don't know, maybe you have to go out and do chores, and then you come back and hopefully your computer hasn't broke. That happened a couple days. That was a little annoying that I let it run. Anyway, so overall, I thought it was a great year. Lots of fun. And I definitely learned a lot of stuff. Hopefully you learned some things too. And again, thank you so much for your comments and your thoughts and the things that you're doing. When you respond or give me comments or just watching the videos, that helps a lot. But it's helping me learn too and be better at it, right? So hopefully, as you know, we keep doing these things, we work on these problems, solve them together, and then it makes us better able to solve these problems further in the future. You know, all of it's about learning. So and that kind of applies with everything, right? I talk to my kids about it all the time. Just like, hey, they say like, how'd you get so good at just programming in general? And it's like, well, I've been doing this for like, I don't know, 25 years. So if you just try and learn a little bit each day over 25 years, you'll be better. So I'm not great at this part of it. I think I'm getting better. But you know, I feel like this is all to say, I feel like this year definitely learned a few new things, learned to improve, make things better. Going to keep practicing, keep working at it, keep learning new algorithms. If you do the same, I promise you'll get better. So there you go. Thanks, everybody. We'll see you next time. Bye.